Alright.
Alright.
So you're on top of a 100-foot building, you throw the ball at 45 degrees and 50 feet per second, and we're going to try to figure out when does it hit the ground.
Alright, so I guess we have, this time our equation is going to be, for the vertical equation is going to be minus 16t squared plus 50 over root 2 t, and then plus 100. So this tells us when we're here and when we're here, we're going to get a negative answer and a positive answer, and we want the positive one.
Ah, okay, so great. So the initial height is 100, and we won't go through the quadratic equations, but solving it, I get negative 1.63 seconds.
So it's over here, we don't want that one.
And I'll call it 3.84.
So, and that's going to tell us, when we use our horizontal, we just multiply this times 50 over root 2, and that tells us our horizontal distance.
What did I say? It was 3.84? Right, so that's 135.8. Okay. Interesting. So it went farther than you thought.
Yeah.
So over here you thought it was going to be falling pretty vertically. It's almost double. That's a coincidence more than anything else. But why do you think it was? What do you think happened differently than you were expecting?
Well, I guess because the horizontal distance, I guess this is an inaccurate real world scenario, so that the ball kept going constantly at the same speed in the horizontal distance. It wasn't getting slowed down, so that gravity would have had more of an impact than it did. They were having the same constant impact.
Okay.
But I think in reality, when we're over here, this is going to be smaller, and gravity's going to have more of an impact because it's going to be accelerating.
Okay, so you think it's actually going to, from air resistance and stuff, going to be slowing down as it goes across this way.
So it won't be going as far this way, and it'll be pulled down. I guess it'll be pulled down the same amount.
It'll be pulled down the same amount, but its speed going down will increase a little bit more. Right, in our idealized model, what's actually happening here is this would also be a 45-degree angle. It's a perfect mirror image. And so it actually is still going out in this direction at a 45-degree angle, at least initially, and then it falls down more and more. So yeah, it turns out it would go 135 feet that way. But it's neat. This is a neat, very, very simple example of a problem that once you've studied vectors and once you've studied a little bit of calculus, all of a sudden you can start solving problems like this and actually making pretty good estimates. I don't think we have any way to measure how fast a ball is going if we throw it, which is too bad, because otherwise we actually could look on a video. We could make a video of ourselves throwing the ball and see how far it goes and how far this little model predicted it would go. I bet it would be pretty accurate. So, alright, cool. Good job, huh?